Okay, so last time, so we are doing conservation of momentum, and make sure you have your final date. You know the date for the final. It's in my FIU. It should be the last week of final, not the last week of class. So make sure you don't miss that. Okay, so let's talk about conservation of momentum. So all the problems that we're gonna work with, you can apply conservation of momentum, but it's conservation of energy depends. Conservation of energy, kinetic energy is only when the collision is elastic. So if you have, so the final, okay, that's good. Okay, so if you have a collision between, for example, a large mass and a small mass, let's say they go heads on, right? The momentum from the large mass is transferred to the small mass. So the change in momentum will be the same for both. But here the momentum is in the mass, so to speak, but the momentum here is in the speed because the mass is small. So this is called an elastic collision, meaning the kinetic energy will be conserved. As a consequence, when you have a collision in 1D, only works in 1D, and the collision is elastic, so kinetic energy is conserved, then the relative velocity stays the same before and after the collision. So for example, here, the relative velocity is 2v. After they collide, it's still going to be 2v. So this one will have 3v relative to this one. It's an approximation. That's when the mass is very large. So anyway, momentum is transferred, the consequence depends on the mass. Sometimes momentum can go in the mass, or sometimes it can go to the speed. Okay, so we did that last time. Here is a demo. You see, they push each other. This one has a large mass, this one has a small mass, so it's a recoil situation. So remember, when you have a recoil situation, you have the magic formula m1 over m2 equals minus v2 prime over v1 prime. So if that mass is 3 times, the speed will be divided by 3. So recoil situation, before the total momentum is 0, so after the total momentum is 0. Okay, so the impulse is the same, right? You cannot kick without being kicked, and you cannot kick harder than you are being kicked. So the impulse is the same, the change in momentum is the same, but because it's going to be mass times speed, here, of course, the speed will be smaller because the mass is larger. So you can see here, push each other. This one is going to go very slow. You can even do the computation with the number of frames per second, and this one is going to move faster. Then another video that I have forgot to, so it's the video of a happy and sad bounce ball. No, one is bouncy, the other one is not. So you have a happy one and you have a sad one. So remember, conceptual question, if something bounces, it's going to provide more kick. Bouncing, more kick, more impulse, right? And there is no sound, which I don't know why there's no sound. Happy, happy. We're going to sand off the string, bring it back, and release it so it hits the block. Question is, what will happen to the block? Will it stay upright or will it fall? In one harness, essentially, with the momentum, the original momentum out. Now let's repeat the experiment with the happy ball. What will happen? Block. So what do you think if it bounces off? What's going to happen to the block? Exactly, right? It's going to provide more kick. The change in momentum will be larger. What? Exactly. Exactly. You can see that at the time too. So the change in momentum is larger, the transfer is larger, so it's gonna have a larger impulse, right? So in boxing, if you want to kick someone, you first it will be the jab, okay? Because the jab bounces off, right? So bouncing off means a quick kick, quick impulse. So it's all physics. And then the other thing I wanted to show you, so that was one. And then the other one is impulse. So when you use the equation, the impulse, it's the force times time equals change in momentum. The force is the average force. That will be by definition. Because to find the impulse, okay, you're gonna integrate the force over time. And if you do that, you're going to find the average force times time. Because each time there is a kick, it cannot be a constant kick, right? It's going to increase, get to a maximum, and then it will decrease. So you can see that here. That will be a kick here. There is a change in momentum because it's bouncing off. The impulse here, the impulse here is the average force times the time. So that will be this area here. So this is by definition. If you go back to my slide, see that will be the average force and you multiply by the time and you get the impulse. And in that case, when it's bouncing off, remember, it has to decelerate. Because it's decelerating, that means the normal force has to be very large relative to the weight. So that's why the force is huge. And what kills, it's not the fall, but it's the landing, right? It's the landing that kills. So it's a very nice website if you like physics. He makes those special GIF. Here it's called Flipping Physics, and he has videos, and I think he has tutorials. It's a very interesting website, but that will be the definition here. You see, integrate. Okay, so what else? Okay, so I don't know where we stopped last time. So the recall situation. The rocket. Okay, for the final, you always you always have one problem about the rocket equation. In your textbook, in your textbook, um, in your textbook, there is a very nice problem. So remember, in that case, you have a bag of tennis ball, right? And you start to throw them forward. And the thrust that you will get, so that means this goes to the right, the thrust that you will get depends how fast you are throwing those balls, right? And how many of them per second. So that's your guts. So let's try if you can find this equation. Um, if we can find the rocket equation thinking of this example here, and you can do you can do the demo, right? You need a skateboard and tennis ball in a bag and see. You have to experiment. Physics, ideally, if you want to understand physics, you have to do the experiment, otherwise it's just memorizing, which is not cool. Okay, so I'm gonna give him a bag. Okay, inside that bag, you have tennis ball, and maybe he can throw more than one at a time. Okay, maybe he has more than one at a time, right? And so that will be the speed with which he's going to throw the ball, right? So as a consequence here, the speed here is going to change. So you're going to have a change in speed here, delta V. Agree? So I'm going to use the conservation of momentum. So the momentum, I'm going to call that mass here, the mass of the tennis ball, delta M. So that will be the amount of mass you have in your hand. It could be 1, it could be 2, it could be 3. So a little bit of tennis ball in your hand. So the change in momentum, why don't you write this down? So the platform with the guy has a mass M. So write that the change in momentum for both system, so that delta M here. So this is delta M. Maybe, I don't know how many of them you throw at the same time. Maybe you're gonna call 3. So that will be delta M. That will be the speed. Okay, so that will be system 1 will be your tennis ball. Right, so change in momentum of the tennis balls here will be equal to the change in momentum of the platform. Do you agree? Okay, so I'm going to say the change of momentum of the tennis ball here will be delta M, and that will be the speed relative to you. Okay, the speed at which you are throwing the tennis ball. Do you agree? Will be minus, okay, the change in momentum of one system equals to the minus, there is a transfer of momentum, the mass of the platform times the change in its speed. Do you agree? Are you with me? Right, it's like Mowgli. Remember Mowgli, delta P1 equals delta P2? It's a consequence of Newton's second law. For every action you have a reaction, opposite, same magnitude. So the change in momentum when two things interact will be always the same because of Newton's third law. Okay, so I have my platform, which is like it's a rocket, okay? It's my rocket here. So it's going to be M delta V equals minus the tennis ball in my hand times the speed at which I'm throwing the tennis ball. Do you agree? And I'm going to divide by the time because the time is the same for both. Right? So M delta V over delta T, what do you think that's going to be? Acceleration, very good, right? So that will be the acceleration of my rocket, quote. So MA equals minus, and that's going to be delta M over delta T times the speed. And MA, so mass of the rocket times acceleration, that's what we call the yes, the force, the thrust. That's going to be my thrust, right? And that thrust will be minus. So that will be the speed at which you are throwing the tennis ball times how many of them per second. So we were able to show that the thrust depends on two things. How fast the exhaust gas is ejected and how much of the exhaust gas per unit second is ejected. So that is called the rocket equation. So each time it's losing. Why do we have delta M over delta T? Because the mass here is going to decrease with time. Okay, the mass of the rocket is going to decrease because you are losing tennis ball or you are using exhaust gas. Yes, it's not conservative, okay? It's a rate at which the mass is decreasing. So think of tennis ball, it's easier to understand. But if you go up in space, so you have the thrust, and what else is fighting the thrust? Gravity, the weight, right? So I'm going to say the thrust. So I'm going to change the equation minus the weight. So at a given time, because it's a function of time, will be equals to minus. And this is really delta M, right? It's really delta M times U. Okay, because that that m here was part of the total mass, so I should write it this way. Do you agree? Are you with me? Isn't now you are a rocket scientist, right? Isn't that wonderful? Yes. It's the speed at which you are throwing the tennis ball. It's a speed, the speed of the exhaust gas. Okay, so let's go back. The change in momentum. So now I'm going to say it this way. The change in momentum of the platform, the rocket, will be equals to the change of momentum of of the tennis ball. Change of momentum of the gas that you are throwing. Agree? So instead of saying delta m, I'm going to say delta m because it's part of it, right? It's just a little piece of the system that you are losing. You are losing mass. Agree? Okay, so buckle up. Are we buckle up here? And we're going to do a little bit of calculus, not very much. So I'm going to rewrite the equation. So U delta m equals minus m delta v. And then I'm going to say, I'm going to divide both sides by m. So I'm going to have delta m over m equals minus delta v. So what can we do with it? Because we can change that into a derivative, right? So u d m over m equals minus delta v. This is not very hard. What is it that you want to do now? That you have a derivative and I want to find an expression. I want to find an equation for the speed of the rocket. Integrate, very good. We have to undo the derivative. And what's the when you integrate 1 over x, what do you get? ln. Exactly. So here I have ln. So I go from mass initial to mass final because as you are losing tennis balls, right, the mass of the rocket or the platform here is going to decrease. You go from an initial mass to a final mass. And you go from final speed to the final speed because the idea is to push on the exhaust gas. So your speed is going to increase as you lose mass. So if I do that, I have a log. So it's going to be ln natural log final, okay, minus initial. So it's going to be a divide equals minus v final minus initial. Do you agree? Because if I do ln of A minus ln of B, you're going to have ln of A over B. Agree? So finally, I'm going to have the final speed of the rocket minus the initial speed equals, it's going to be U, the speed at which you are throwing ln initial over final. Are there people talking? Think about it. When you do a minus, that's not fair. Okay. My handwriting is terrible. Okay, any question? Yes, yes. Yes, but when you do minus ln of A over B, you're going to have ln of B over A. So with the minus, I flip here because you always go initial over final. Initial will be positive and initial will be always larger than final. Any question? Okay, so that's the rocket equation, and definitively in the final you have one question, and in your book they are very good with it. Okay, so that's textbook. You see, 815, 816, that's how rocket works, right? The change in momentum for the gas will be equals to the change in momentum for the rocket. However, most of the momentum here is in the speed, most of the momentum here is in the mass. But the change in momentum is the same. Okay, so then I don't know where I am. I'm lost. No, just yeah. Okay. No, it's good. So, conservation of momentum, remember that momentum is a vector. So, you want to make sure that the momentum is conserved, but you have to remember that it's a vector. So, for example, this is possible with high speed photography. So, you shoot or someone shoot at an apple, for example, and not only you're gonna have stuff coming forward, okay, that's here the momentum is huge because even though the bullet has a small mass, the speed is very large. So you have a large momentum. Momentum is a vector. It's going to be important for conservation in 2D. Okay, the vector momentum, the total momentum before equals to the total momentum after. So you need to have the vector, same magnitude and same direction. So before here, the momentum is a very large vector. After, it's even larger because the bullet didn't slow down that much, but now you have stuff. You have the pulp, right? So that will add up. But that violates conservation of momentum. It doesn't go well with nature. Nature says, no, 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 it cannot be. You see, that momentum after cannot be larger than the momentum before. Are you with me? So we need to have stuff coming from the back, and that's what it does. If you do a high speed camera, you see stuff from the back. So it's like the apple shooting the bullet with some recoil. Isn't that crazy? And you can see that only we know how to do high speed photography. So there is a connection here to make with JFK. We will never know. And assassination. So there is a big controversy because they say when you look at his skull, right? When you look at his skull, yeah, there was stuff coming from the front and stuff coming from the back. So at the time they said, oh, this is the proof that you had two people shooting, two shooters, right? One for the back and one for the front. And then you have a genius, and it doesn't nail it down. It's still not sure really what happened. Obviously, they don't want us to know exactly what happened, but nevertheless, there is a genius. His name is Luis Alvarez. I don't know if you heard about him. He's a particle physicist. He got the Nobel Prize because he worked on the hydrogen, no, the bubble chamber, right, to detect particles, and he was able to show that out from nowhere you have new particles popping out of space, right? It has to do with quantum physics. So anyway, he got the Nobel Prize. Super smart. He worked on the atomic bomb as well, and he did this very famous experiment where he took like a watermelon, and it was before high speed photography, and he shoot like with a rifle, and you have all this stuff coming forward, but also stuff coming backward. And before that he used a duct tape to make like the skull. So his point was, it's not because you have stuff coming from the back of the head of the president that you have only that you had two shooters, right? It could be just one because of conservation of momentum. So it's a very famous experiment. There is a website that explained that. Luis Alvarez, right? He used a watermelon Warren Commission and blah blah blah. So it's interesting. So my point is, I don't know really what happened. Nobody knows, but my point is that uh, that's physics. So you expect stuff from the back and stuff from the front. So that's a nice illustration. Okay, so let's do easy stuff and go back 105. Okay, let's do number one. It's easy. Go back and forth. Go back and forth. So for those who just came, don't forget test number 3, okay? And I will extend till tomorrow morning for those who have who are early bird and they don't like to work at night. So this is about full back. I can understand what a full back is. 100 kilogram and going west. So he's going west. So west. So here 3.5. So defense, they're all back. I don't know why it's all back. So defensive back, and you have a line back and whatever back. So plus, minus, and this one is going 6 meters per second. So already, if you do the multiplication, you know who's gonna win. Okay, so I'm gonna call that number 1 and number 2. So that's before, right? And so after they stick to each other. And let's say we don't know which way it's going, although we know because that will be 350 and that's 480, isn't it? No. Okay, so this one will win. Okay, so momentum before, so 100 times 3.5. Here you have to be careful because it's negative. Okay, after you have 100 potatoes plus 80 potatoes. So 180 potatoes, right? So 95. Is that right? What is negative 130? Yeah, 350 minus 40. So this is not 95? Negative 130? Okay, thank you. So V prime equals minus. Do you agree? Yes. So it's moving to the left because this one is winning, right? So 0.72. And I didn't answer the question, right? So P1, the momentum of P1 is 350 kilogram meter per second. Momentum of P2, 2 is minus 480. So this one win. So the total momentum before that stays the same. Okay, it will be so negative 130 before and after. Yes.
And you know which one got up front and which one got next.
What do you mean? This one goes west, so I decided west is here.
Oh.
Right? Huh?
It's the other way around, shouldn't it? 80 kilograms heading.
Oh, you're right. Dyslexic here, west and east. Okay, it's fine. Pretend west is here and east is there. I missed up east and west. Right. So it's let's say this is west and this is east. But the winner is still the same. So if you do the opposite, that will be positive. Okay? Do you agree? Okay, let's do a quick recoil situation with the magic equation. So it's a recoil situation, right? So we have magic equation for recoil, something like this. You see, it's opposite. So before they don't move, and after they move. This one has a small speed, and this one has, and the ratio between the mass and the speed is the same, right? Plus, minus, after. Let's call this one number 1, and this one is number 2. What is the total momentum after they push up? So what is the momentum before? They don't move. So it's 0, right? And that will be the momentum after. The total momentum of the system is 0. That means it's a recoil situation. The larger guy, skater, doesn't have to be a guy. So this one is 3 meters per second, and this one IDK. Agree? So what? Either you do m1 plus v1, m1 v1 plus m2 v2 equals 0, or you use the magic equation. I'm going to use the magic equation. So AT over 32 equals minus v2 prime idk over v1 prime. It's minus 3 because left is positive. So v2 prime equals 18 times 3 over 32. Agree? An equation 80 times 3. What is that? 0, 0.5?
7.5.
7.5. Thank you. So it's the same ratio for the mass. My calculator. Okay, question? Good. Okay, let's do this one. It's a quick one. So it's a collision. So this one is easy, right? It's hit and stick. You have the recoil, you have the bouncing, and you have hit and stick. So you have a 12,000 here. It's moving, and this one is not moving. So that's before 12. So after, they stick to each other, right? So you have one mass. It's one big mass, right? It's like the ball, that the sad ball. So you increase the mass, so the speed will decrease, and the mass is the same. What's the initial momentum of the first car? So you multiply, right? So it's going to be 12,000 times 12. So that's going to be 144,000. And that will be also the total momentum before. So the total momentum after should be the same. Agree? So the total momentum after equals, and you have 12,000 potatoes plus 18,000. Yes, so 30,000 potatoes. You go bye bye, bye bye. So V prime equals 144 divided by 30, which is 4. Question? So it's a review, right? And make sure to go and do the solve problem in the textbook. You have to hide the solution. You need to hide the solution. If you look at the solution, it's not going to help. You have to hide and try to do it on your own. Okay, let's try to do a picture, a drawing. So you have baseball. Like, I don't understand baseball either. So 40 meters per second. And then someone is going to hit the baseball with a baseball bat. The baseball, so this is 0.12. Okay, we don't know here. So that's before. Do you agree? And then it's bouncing off with 60 now. So you see the kinetic energy has increased because there is a transfer of energy from the baseball bat. But the total momentum stays the same. Total momentum stays the same, but the kinetic energy here has increased. Okay, there is a transfer of momentum. Kinetic energy has increased here and the momentum has increased. So if this one has increased its momentum, that means that the momentum from the bat has decreased, right? So that means there is a recoil. This baseball bat better recoil to make sure that the initial momentum, total momentum stays the same. The momentum of the baseball bat will go to its mass, but the total amount of momentum will be the same. Okay, so what do they want? The mass, they have the time. Okay, A. What is the change in momentum of the baseball? So P, so this is thing number 1, that will be thing number 2. So change in momentum will be the mass. Do you agree? And here we have to be careful. This is plus, this is minus. So left minus will be minus 60, minus 40. So remember for a test, right? When something is bouncing off, you add. You're going to add the speed. Bouncing off, you add the speed. So that will be minus 12. Right? Do you agree? So the change in momentum for the baseball bat will be the same, except that it goes to its mass. So you have a recoil, but the speed is smaller. What is impulse? So the impulse is the same, right? The impulse by definition is the change in momentum. So that's going to be minus 12. You can change the units if you want. So if there is a change in momentum, that's because there is a kick. So the baseball kick the bat and the bat kick the baseball. Kick is the same. The change in momentum is the same. Number C, what will be the average force, right? Can you do that? So average force times the time of impact equals the impulse, which is the kick. And you have the time. Is correct? The average time, the average force. So the force will be, yeah, very good, 300 Newton. So that's the kick this way, to the left. But that means that the bat is also experiencing the same kick. The same kick. For every action, you have an equal opposite reaction, but because the mass is really big here, the speed will be small. But the change in momentum will be the same. Agree? So which one experienced the most momentum? Something that crash or something that bounce? Bounce, very good, right? For the same mass. Bouncing, more kick, more kick, more kick. Okay, let's do the little girl. Because little girl are cute until they are not. Okay, so try to do it. So first you do the drawing, right? You can help each other. Do the drawing first and see what you can do. That's before. So both of them are at rest, right? So what type of situation do we have here? Recall situation. It's a recall situation, right? It's when you go kayak and you go inside the kayak and all of a sudden the kayak like happens. Okay, so I'm gonna call the little girl number 2. Okay, so I can use the equation, the magic equation, right? So 1 is 20 over 35 equals minus V2 prime. V2 prime over minus 3.8. Do you all agree with that? So V2 prime equals 35. Yes, 2. So M1 over M2 equals minus V2 prime over V1 prime, and we want the speed of the little girl. because it's the wagon. Yes. Do you all do it? You find something like 2, right? Okay.
Thank you.
Go positive because it's positive.
Oh, it's the initial.
One more, number 2. Number 2, a limousine. There is a story of a limousine here. Number 2. Basketball. Boom, boom, boom. So do it at the same time, so that way we review for the final. We are reviewing for the final, right? Hit. So 12 kilogram. So that's before. So number 1, number 2. So this one is going to move forward. And the other one is bouncing out. Okay, da 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 da. So this way, it's moving here at 3.8. And some of the momentum has been transferred to the wagon, but it goes to its speed, right? Okay. So total momentum before, so that's going to be 1.2 times 7.5. And here, typical mistake, you forget that it's moving to the left. So it's going to be a negative, right? Momentum is a vector. It can be negative. Now that will be a typical mistake, because if you don't put a negative, then you're going to subtract instead of adding. Plus 12 times V2 prime. Okay, that's the only challenge in kinematics in 1D. In 1D is to make sure that you have the negative if it's moving to the left. So V2 prime equals, I found that now. Yes, I'm lost. Okay, good. Okay, and then typical, classical, it's called the ballistic pendulum. So before high speed photography, and that's where they were able, that's how they were able to find the speed of a bullet. So that's the main idea, right? To find the speed of the bullet. So you shoot in a block. The block here is hanging. So you have a pendulum. You're gonna have a pendulum, right? So the bullet goes inside the block, and then it's gonna go up. So let's see, pendulum, ballistic pendulum. Same website. You see, it's gonna go to increase the height, and So by finding the height, the question is, how can you find the speed of the bullet? So first of all, let me ask you something. Can you use conservation of energy between step 1 and step 2? Why or why not? Is the energy conserved? Yeah, so it's not conserved because of some of the kinetic energy will be lost the to well, how friction, right? How do we lose energy? Is if you have air resistance, if you have friction. So because the bullet is gonna rub inside the block is gonna have an increased temperature. So you cannot use conservation of energy between step 1 and step 2. Okay, because you don't know how much energy has been lost to heat. Agree? However, can we use conservation of momentum? Yes, it's heat and stick. So between step 1 and step 2, we're going to use conservation of momentum. Step 2 and step 3, what's happening here? What is it that you can use? What type of energy does it have? So yes, so kinetic energy, and then all that kinetic energy is going to turn into potential energy. So we're going to work backward, meaning we start from mgh equals to the kinetic energy here, right? And then we use conservation of momentum to find the speed of the bullet. So that's the main goal, is to find the speed of the bullet. And that's how it was done before high-speed photography. So if you go to YouTube, you still find people they know how to use them. So it's called a ballistic pendulum. So I'm gonna go from step 2 to step 3. So this is conservation of energy. Okay, so I have the total energy before, which is kinetic energy. Okay, so the mass of the block plus the mass of the bullet. So 0.5 mv squared equals the total mass times the potential energy. So this is kinetic energy equals to potential energy. Do you agree? If we neglect a resistance, and you see it goes bye-bye, which makes sense because it's in free fall. If you have a pendulum, the period of a pendulum, right, the time for one cycle does not depend on the mass. It depends only on the length of the pendulum, not on the mass, because it's in free fall. So mass does not matter, said Galileo. Okay, and you have this famous equation when you have from kinetic energy to potential is going to be the square root of 2gh. So that will be my second equation. That will be the speed of what? This speed here. The speed of the block here. Do you agree? So that's conservation of energy. And then you have conservation of momentum between here and there. Okay, so momentum before is going to be mu equals momentum after, so it's going to be the total mass, so it's stick, heat and stick times v. So you have two equations with two unknown, and so you can isolate the speed u. So u will be equals to m plus m v over m. So that will be the ballistic pendulum equation. So again, and I forgot h somewhere. No, it's good. Okay, so the velocity equals square root of 2gh, and that will be the speed of the bullet. So first you find the velocity and then of the block, and then you find the initial velocity of the bullet. Do you all agree? So we have to use both equations. Agree? So let's take a easy example. Let's take an example. This one. Yes, you use this equation first, right? So that will be the speed of the block. The speed of the block equals square root of 2 times g times the height, 0.650. So you do that first, right? So try to do it. If you have any question, let me know. Don't take notes, because then by the time you get home, you will forget about everything and you won't be able to understand your notes. So if you have any question, let me know. So 3.6 meter per second, that will be the speed of the block when they move together. And number one, then we can solve for the speed of the bullet, which is the block, which is 2.5 plus 0.01 times 3.6 divided by 0.01. Do you all agree? You can even neglect like 0.01 because it's so small relative to 2.5, but you have to keep it here. So you get, so I think it's also in the final, I forgot, but you get something like this. Yeah. So that's 2000 miles per hour. That's more than the speed of sound. That's why you hear that bang. I, any question? So it's again, I really, especially if you want to go to engineering or physics, yeah, you have to use a textbook. They have very nice problems there. This one is from an algebra class. Twice the speed of sound. So elastic collision, again, conservation of momentum, conservation of kinetic energy. And if you massage and malax, those two equations, okay, so if you massage and malax, conservation of kinetic energy, conservation of momentum, you get to this equation that I told you about, right? The relative velocity stays the same before and after with a minus sign. Okay, so it's a trick. So you can solve quicker, right? So again, elastic collision, the total amount of kinetic energy, so before, equals the total amount of kinetic energy after. And you should play with that. You have to use v square minus a square minus b square, whatever, and you get to this. Okay, so the relative, it is in the assignment, so the relative velocity stay constant, except there is a minus here. And I gave you the example of the basketball and the tennis ball. Okay, so if otherwise, if you do the computation, that will be what you get at the end. So in some of the problems are very complex, so you have to do it in different steps. So for example, between steps in this complex situation, typical of a bumping car, bumper, I don't know what it's called. You see between here and there, here you have, what type of energy do you have here? What type of energy? what type of energy do we have in step one? Kinetic energy, right? So we can find the total amount of kinetic energy, right? 1/2 mv1 square plus 1/2 mv2 square. And what type of energy do we have here? So it's still moving. So you still have kinetic energy and, huh? Store, so it's called L, elastic potential energy. Okay, so the total amount of mechanical energy before equals the total amount of mechanical energy after, elastic plus kinetic. So that will be one equation. Second equation, between 1 and 3, you have conservation of momentum. And then you just have to pull your hair with algebra and solving equations. But the physics is easy, right? Conservation of energy, conservation of momentum. Okay, and then in 2D, then it becomes even more algebra, right? Because then you have to decompose the motion along two axis, x-axis, y-axis, right? And you have to say, okay, momentum is conserved along the x-axis and momentum is conserved along the y-axis. So you have to remember that momentum is a vector, right? And it's heavy in math. So it means, like, when you have a collision like this, you see this angle doesn't have to be the same that one, but you know that the momentum before, right? The momentum before has to be equals to the momentum after. So you have P1 here, and let's say you have P2. When they're gonna add up, because these are vectors, you're gonna get the same before, and that's P after. The momentum has to be the same. Okay, so the total momentum before has to be equals to the total momentum after, but you need to use vectors, adding vectors. So you can add the components. So the total x component equals to the total x component after, y component before equals y component after. Got that? But the idea is that you can do that, like in a lab, you can do it using vectors. So the total vector before equals the sum of all the momentum after. Agree? And it's just a headache. It's just a lot of math. Like you see, you have to use the cosine here, and you have to use the sine, so you can look it up. You can use your textbook. I'm not going to do it because it's just math. But the total momentum before equals the total momentum after. So it's a vector. So the typical situation here, they hit and collide. So the total momentum before equals the total momentum after. So if you have a P1 here, that's the car, and you have another car P2 here, right? So you can do P1 plus P2. That's going to be the total momentum before you add the vector. So that will be P before. So when they collide, they're going to move together, but the total momentum has to be the same. Okay? It depends, because if it depends on the angle, and it depends on the car. This one is heavier. Because this one is heavier, it's going to push more in this direction. The winner depends on the mass, right? So this one is heavier, so the angle will be more than 45 degrees. If they have the same mass, and the same initial speed, then the angle will be exactly 45 degrees. So it depends on the initial momentum. So if this one could have more momentum if it goes very, very fast, so then the angle will be less than 45 degrees. It will go in this direction because that will be the winner. But when you add the momentum before, so those two vectors will be equals to the momentum after. And you do that with components. Agree? So it's always there is still a story with the winner, right? The one that has more momentum will win. Momentum. Let's say they have the same mass. Okay. So let's see what will happen. The same speed. You see, the angle is 45 degrees because there is no winner, right? So if we make one bigger, so more momentum for the same speed, so the angle is more than 45 degrees. Does it make sense? If this one is larger, boom, right? Now you can make this one very big, but this one we can make it very fast. Let's see which one. Oh, so they have the same mass, but the red one wins because it goes faster. So it's not just the mass or the speed, it's the mass times the speed, more momentum. So if boxing, you have something called the cross, that's because you add the mass to the body mass. So that will be a huge momentum that goes into hitting someone. Okay, so you can see here, yeah, I recommend that you go over those slides and you see how it's solved. It's a lot of algebra. Okay, any question? Okay, very important now, new unit, and we're going to talk about torques. A torques, so far we have seen linear motion, and now we're going to see rotational motion, right? So a torque, you can think of a torque as a twist about an axis of rotation. A torque is a physical quantity that will measure how efficient you are in applying a twist about the axis of rotation. So you have the effort, right? Push, that will be the effort, and here you have the load. So each time you apply a torque, well, we're going to see that in more details. So rotational equilibrium also very important for civil engineering. So you have, in that case, for example, this is a translation motion. And here you can have a complex motion where you have translation and rotation. Interestingly, the center of mass only responds to the external forces. So the center of mass doesn't care what you are doing, right? It only responds to external forces, so only responds to gravity. So the center of mass will follow projectile motion. So anyway, I'm going to do that in a nutshell. Rotational linear. I'm going to compare them together. So let's look first at kinematics, and we're going to review things that we have seen before. Okay, so rotational motion and rotational dynamic, it's not easy. It's challenging. It's counterintuitive, and it has very weird effect. Like gyroscope is an example. Counter steering is another example. So it's very interesting, but very weird as well. So I'm trying to to do it in a nutshell. So linear motion, remember we did, I'm going to compare, let's see, I don't know where to compare. Let's see. I'm going to go here, right? So linear motion, we had the position on the number line. Yes? Do you agree? Okay. That was the position on the number line. Now for rotational motion, we're going to work with the polar graph, right? So this is 0 pi over 2 pi, 3 pi over 2, 2 pi. And here, that will be called the angular position, and the unit will be in rad. Okay? And you always go counterclockwise. So you always go this way. So for example, pi over 3, that will be 60 degrees. So you take, see, I brought this, you take that polar graph here, right? You put you aim at 60 degrees. That will be the angular position, pi over 3, right? And you can have a radius, the radius r. Okay, and then we have the displacement. So for example, here we can go from x1 to x2. So you can define the linear displacement, right? So that will be the linear displacement, or you can define the distance between x1 and x2. So the distance will be, it will be a linear distance, right? So you go from, so that will be displacement. Okay, let me do another thing here. So you go if you go from S1 to S2, you can find the distance, S1, S2. Okay, so the distance you have to measure the path. Do you agree? So this is called the linear displacement. This is displacement, this is the linear distance. Linear distance, linear distance. We good? Okay, so here in the polar graph, you go from angle theta 1 to theta 2. You go from here to there and you go counterclockwise. So delta theta here will be called the angular displacement. So this is called the angular displacement. Okay, so that will be in rad. So you go from here to there. Do you agree? Right? You go round, you go from this angle here, 20 degrees to 80 degrees. 20 to 80, that will be 60. So pi over 3 will be the angular displacement. So far, so good. So between here and there, so this is the radius r. So between this here, that linear distance here. So this distance here is linear. So I'm going to call that d. So that distance here is r times this angle there. Okay? R multiplied by r. Do you agree? We already did that, right? So if you go, for example, the circumference, you go around the circle, so it's 2 pi r. So if you want to have the linear distance, you multiply the radius by the angle here in radians. So this is in meters, this is in meters, and this is in rad. Agree? Are you with me? There is nothing new under the sun, right? We already seen something like this. If you go all around the circle, the distance around is just 2 pi r. So you multiply the angle in radians times the radius. Any question? Okay, this is very important. So it's just that I'm not, I took too much space. Okay, next we have the linear speed. So linear speed, okay, is going to be the distance divided by the time elapsed. I'm going to call that V. They call that V. Okay, so that will be your linear speed, not the velocity, right? The linear speed. Okay, now for rotation, you're going to have the angular speed. So this is linear. And then you have angular speed. So what is angular speed? Think of revolution per minute. So the old vinyl from my time, that was 33 revolution per minute, right? Or 45 revolution per minute. So RPM. So how fast it's spinning. How fast it's spinning, it's called the angular speed. The notation is omega. So omega is by definition the angle that is swept divided by the time elapsed. So it makes sense, right? So for example, 33 revolution per minute. One revolution is 2 pi. So 33 times 2 pi divided by 60. The unit here is rad per second or RPM. Agree? So stay with me. That's going to be very useful. Okay, so we have the linear speed. This is the linear speed, and this is the angular speed. And now you have a relationship between them. What do you think the relationship is? So V equals, okay, I'm going to help you. So we know that the linear distance is r times delta theta. So if you divide both by the time, you're going to have the linear speed equals r omega. Okay, we already seen that equation. It just means that farther you are from the center, faster you're going to move, right? Let's see. Okay. Does it make sense? So do they have the same rotational speed or angular speed? Yes, they are spinning at the same rate, meaning they are sweeping out the same angle per second or the same number of revolution per second. But do they have the same linear speed? No, because during the same time, the one at the edge, okay, is covering more distance. So the rate of spinning is the same, but not the linear speed. And you see, you have the equation here. Linear speed equals radius times the rate of spin. So twice the radius, twice the speed. Okay, so people at the equator are spinning faster than the people at the pole, right? You can see that here. You can do that. It's not easy to do that demo. It's come from flipping the physics, right? So this guy is moving faster. This one is not moving. What's the linear speed of the guy at the center? 0, right? He's not going anywhere. So the spin rate is the same, but not the linear speed. Okay, so we have this relationship here. Okay, now omega is the rate of spin and it has a direction. So if you look at my hand like this, I'm going to put the thumb here. If it's rotating this way, the rotational speed is a vector and it will have the same direction as my thumb. Okay, so if something is spinning like this, you have to use your right hand. If you spin this way, if it's spinning this way, let's say it's spinning that way, okay, so spinning that way, the vector angular velocity will go towards you. So it's also a vector. Okay, so it's here you just have the magnitude, but it does have a direction as well. It's a vector. So I don't know if I have a picture here. Here we have one angular velocity. I should say angular velocity, not angular speed. If it's spinning this way, you take your right hand and the thumb will give you the direction of that angular velocity. Are you with me? It's going to be very useful when you want to understand gyroscope and angular momentum. Okay, spin momentum. Are you with me? So in that case, it's up. It's a vector. Agree?
Straight down too.
Yeah. So if it's spinning this way, it's gonna go this way, right? If it's spinning that way, it's gonna go that way. This way is gonna go this way. So, and then you have the angular, the acceleration. So acceleration, remember, it's going to be delta v over delta t. Okay, it's a vector. So here we're gonna have also angular acceleration. How fast it's spinning faster. So in magnitude, the acceleration, the angular acceleration will be same thing, delta omega over delta t. And see here, now I'm using a vector notation. Why? Because if you have an acceleration, that means there is a torque, or there is a, to get an acceleration, that means we need a torque. So anyway, my point is that the acceleration here has also a direction, and I'm going to show you why. But do you agree with me? Okay, so now you have the angular acceleration, and it's going to be equal to delta omega over delta t. If I use the magnitude, you have the relationship linear acceleration equals r alpha, and this is alpha. So you still have this relationship. Okay, you have the same relationship for the distance and the angular displacement. You have a relationship between the velocities. So we have this relationship here. Okay? So this is very important because we won't have time to do too much of rotational dynamics. So I do it in in a nutshell. So you see here, when something is spinning, the velocity here has a direction. Now you can have an acceleration. That acceleration will make it go faster, slower, or change direction in that case. You see the rate of speed is increasing, so it's spinning faster. There is an acceleration, that means it's spinning faster. What about if the acceleration is opposite? It's going to spin slower, right? Same thing for linear motion. It's going to spin slower. But this is where it gets interesting. What's going to happen here? Is it spinning faster or slower? No, you are changing the direction of the spin. So imagine this is your acceleration. It's like a force, right? That will be your torque. What you are doing here, you are pushing the speed. So it's going to spin faster. Here it's going to spin slower. Here you are changing the orientation of the spin. Okay, so this like you are biking at the same speed. The wheels are spinning, and all of a sudden you use like you do this right on the side. All of a sudden your wheel will not go faster. The wheel does not go slower. The wheel just make a turn on its own. Okay, so it's not that easy to understand. So let me show you that here last time. So I can make it spin here. I can make it spin faster. I can make it spin slower, right? Slow it down, or I can change the orientation of the spin. Not easy to understand. Are you with me? So think of a bike. A bike, you have the wheel. The wheel, you can make it go faster because you're applying a torque. You can slow down, just leave friction to its work. Or you can lean to the left. You lean to the left, and all of a sudden the wheel will turn on its own. You change the direction of the rotation. Okay, I stop, right? Do we have at 12? Do you see something? At what time is this? 12:04. Okay, I'm going to try to change it.